All right, today we're going to take a look at a solid ball rolling down a hill, and I want to figure out the acceleration of this sphere as it goes down the hill. But before we do that, let's remind ourselves what would happen if this sphere were on a frictionless surface. If the surface were frictionless, the sphere would not spin. It would just slide down. If that were the case, the only two forces acting on the sphere would be the gravitational force toward the center of the Earth and the normal force, which is perpendicular to the ramp. The ramp is in this direction. That's a right angle. The only force in the direction of the motion down the ramp would be mg sine theta. We set that equal to ma because it's the net force. So the acceleration would be g sine theta. And that's true for any object sliding down a frictionless incline. All right, now, this sphere is going to spin. And in order for that to happen, there has to be a torque applied to it. And the force that creates that torque is friction. Okay, so if there's a friction force up the ramp, the ball will start to spin. Now, what we want here is we want the ball to roll and not slide. So if there's not enough friction, the ball will roll a little bit, but it'll still slide some. So we want enough friction so that the tangential velocity at the edge of the ball and the velocity of the center of mass are the same. All right, so if that's the case, if I add in a friction force here, actually I won't do it here. So if there is friction, we've got a gravitational force, we've got a normal force, now there's a friction force up the ramp. Okay, now first thing we want to recognize is that that friction force is applying a torque. So if we do the radius cross the friction force, that equals I alpha. All right, now let's simplify this a little bit. So RF sine 90, and so since it's cross product, it's the magnitude of R times the magnitude of F times the sine of the angle between them. So if this is R, friction's up the ramp, they're at a 90-degree angle to each other. All right, equals I alpha. For a solid sphere, I is 2/5 mr squared times alpha. Okay, so the sine of 90 we know is 1. So on the left-hand side, I just have R times F. On the right-hand side, I have 2/5 mr times R alpha. All right, I want to group it that way together because R alpha equals acceleration. Now, once I do this, I can simplify this. I have an R on each side, and the friction force, the size of the friction force is going to be 2/5 ma. All right, that's the right amount of friction to make this roll without slipping. Okay, now we're going to hold on to this. Now, the center of mass of the ball is also accelerating down the ramp, right? So the net force in the x direction is ma. And I'm going to make a little note. It's the acceleration of the center of mass. Now, if we add in friction, so we've got mg sine theta down the ramp. We've got friction force up the ramp, okay? So let's simplify this a little bit. So ma, I'm going to make a line here so I don't mix these up. ma equals mg sine theta minus f, which is 2/5 ma. Okay, there's an a, there's an, actually, let's add 2/5 ma to both sides. So 1 ma plus 2/5 ma is 7/5 ma. This equals mg sine theta. There's an m in both terms. Multiply both terms by 5/7. The acceleration equals 5/7 g sine theta. All right, which makes sense, because if none of the gravitational potential energy went into rotational kinetic energy, we've got an acceleration of g sine theta. Since that's happening, our acceleration is going to be a little bit lower. It's not quite g sine theta, it's 5/7 g sine theta.